Hi, this lecture is an introduction to an aspect of electric current referred to as the current density. So the current density is going to be given the symbol capital J. And let me tell you that the current density is itself going to be a vector, and it in general can vary over space. It can have a different value at different coordinates in space, as well as a different value at different times. But for this chapter, we're not going to consider current density J being time dependent. But it is true. The current density can fluctuate, change in time. But for the purposes of this chapter, we're just going to consider the fact that J can vary over different locations in space. And yeah, so this is J. There is a basic relationship that the current that flows through an area A, it's equal to the integral of J dot dA, where it kind of looks like this, like yeah. So I'll get to this in a minute, but let me show you some more about J. So here's the idea. Imagine you have a river, right? So here's a river, and the river is, let's see, say blue water. So if you have a river, the water is going to be flowing along the river. So here is a sense of the flow lines. If there's a rock in the river, let's put a boulder, right? So here is a rock. What this does is it creates an impediment for how the water can flow, because the water can't flow through the rock. So as the water comes up here, it's going to divert, go above or below. But the truth is the flow pattern can be really interesting. So it may go up and over, but behind the rock, you can get what are called eddies, right? Eddy currents. You can have places where there is no flow at all. It's almost like the water stands still, and if there was a leaf or a stick, that stick might stand still here or sit and spin around, right? Neither leaving the location nor yeah. So, but the point is the flow can be different at different places. So you might say that the flow here is 0 because it's not flowing. A leaf can stand still. And the flow here can be very, very strong at the constriction. And the flow out here can be kind of weak. And more than that, the flow here might be in this direction, and the flow here can be in this direction, and the flow here can be in this direction, right? So the value of the current flow is different at different places, right? Including have value 0, including going backwards, right? It's going backwards to the main current flow. But overall, if you imagine drawing our little ammeter line, right, and having somebody sort of count the gallons of water passing by, they should be able to describe a current that flows past their sort of like boundary line. And the way that this person counts up the current is this way. They're going to imagine that flowing across their boundary that they pay attention to, that the current density J is piercing this cross-sectional area, adding up a total current across that area. Okay, so this is the idea of the current density J. Oops. So here's an interesting thing. So J is a vector. Let's wonder about its units, right? So the current is going to be in amps, for example, the SI unit, and it's the result of adding up a bunch of areas, right? Which in SI unit is meters squared. So that means that J times meters squared is amps. So it must be that J could have units of amps per meter squared as its SI unit, right? So the current density is a current per area. So an interesting thing to do is to try to model J this way. So this is a typical model. It says to take something called N, multiply by something called E, and then multiply by something called V sub D. So let me tell you what each of these things is. V sub D is what's known as, the drift velocity, right? So lowercase d is for drift, and it's a velocity, and notice that it's a vector, right? You see the vector symbol above. So velocity in general is a vector quantity because direction is important. This is the drift velocity of the charge carriers of the electric current, right? So the idea is I have these little electrons, for example. If it's electrons, then I'll have to put in the charge, or actually, let me pull back from there. So let's just square this off. So I've got the drift velocity. It's the velocity of the charge carriers that form the electric current. E is the charge of the charge carriers, right? So typical electric current, the charge carrier is actually electrons, right? So you would put in, for this value, if these were electrons, you'd have to put in 1.6 times 10 to the minus 19 coulombs with a minus sign as the charge of the charge carriers in a typical electron current. So notice that the charge is negative, and then this is the amount of charge that one electron has in the SI unit of the coulomb, right? So it's got a really small amount of coulombs, right? One electron actually isn't very much charge. But then N is the number of charge carriers per volume. So in terms of units, this thing right here, SI units, for example, are meters per second, right? It's a velocity. The units of the charge of the carriers is going to be in coulombs. And then the units of something like this, the number of charge carriers per volume. So whenever you say the number, that strictly is purely a number with no units. But then there is the per volume. So what N is going to be units of 1 over meter cubed. So what does this look like? If I say that J is equal to NE drift velocity, like this, N is 1 over meters cubed, right? Let's just study the units. So N is per meter cubed, E is coulombs, and velocity has units of meters per second. And if you multiply these three things together, the units of J, right? You see it. Let me change colors. The meters, one factor of the meter cubed cancels with one factor on the top, and I get coulombs per second 1 over meters squared. And this is current divided by area, which is what we're claiming J is. But the point is this is how we are going to model the connection between what we say is called a current density, called J, right? Its relationship to the electric current, which is not the same thing as current density. Current is just plain old amperes. But what we want to do is we want to imagine the fact that the current in the wire can be different at different places in the wire. And if we want to imagine different values of current density at different places, then that's a microscopic model of current. The thing is I itself is something of a macroscopic idea. It's sort of an average idea or a total idea. But if we want to model electric currents based on materials, that is, are we talking about a current in copper, or are we talking about a current through a junction diode in a piece of electronics, right, that's very special, then we don't want to think in terms of this crude, sort of macroscopic, large, average idea. We want to think in terms of actually materials ideas, like what is actually the motion of the things that are moving, right? Those are called velocities. What is the thing that's moving? And how many of them do we have in our material, right? So if we come up with, or if we have this interesting model, then we can begin to think microscopically or fundamentally. It's a fundamental perspective on what's going on, right? So this is something that you should work out a way to sort of like think in terms of. So I have an example. The example looks like this. So here's an example. So imagine that I have a wire. All right. And the wire actually has a cross section that is a square. I hope you can sort of see what I'm drawing, right? So it's a 1 centimeter square cross section. Wire, right? So this is 1 centimeter by 1 centimeter. And current flows, let's say in this direction, right? So that will be the current flow. Let's say that the current flows non-uniformly. So whenever I describe that it's non-uniform, it begins to require a description that's based on a coordinate system, right? Because if it's non-uniform, that means it's not the same at all the different places. So what we need to have is a way to keep track of the different places. So I'm going to include a coordinate system. So this sideways direction is the x direction, and this vertical direction is the y direction. And let's say that this direction, which is the direction in which the current is flowing, it's got to be the z. If this is x and that's y, then this is the positive z direction, like that. All right. And so I'm making this up, but I'm giving you an example problem. So let me make something up. I'm going to say that the current density is a value which actually only has a y dependence, right? So instead of it being a function of x, y, and z, I'm going to just say that the only thing I need to tell you about is its variation in the y direction. So it's the up-down direction in the diagram. And I'm going to say that the value of j as a function of y, it's sort of strange, but you'll see the units will end up working out. So the units in this particular example are, so I'm going to say it's 2 microcoulombs, right? Microcoulombs. It's divided by centimeters cubed times the second times y, right? So that's the y variable, and it's in the k hat direction. So that's j. So j is moving, right? It represents current density flow in the z direction. That's what k hat is in unit vector notation. Okay, so now here is the example problem. What is I on this wire? So I is the integral of j dot dA, and so the current through the area A is this, right? This integral. And so the area A that I care about is all of this, right? That's the area A, because I want the current on the entire wire, right? I don't want the current on the left half or the top half or just down the middle, bounded by some small piece of area. I want the whole area. So, but because j, right, depends on y, when I do this integral, I'm going to have to treat y in a special way. And the way I'm going to do that is I'm going to imagine going in and just studying strips of area that go across like this, right? So that's a strip of area, and the strip of area has a height of dy, but a width of 1 centimeter. Can you see that if I go from y equals to 0 all the way up to y equals to 1 centimeter with these strips, then I'm going to be able to do the integral. So let me do the integral that way. So it's going to be the integral as y takes the values from 0 up to 1 centimeter of j, which is 2 microcoulombs per centimeter cubed times the second. It's y, k hat, right? That's all the information about j. And then I'm going to dot with an area vector, a small area vector, but the small area is dy tall by 1 centimeter wide. So it's 1 centimeter times dy. That's an area, but the area vector also points in the k hat direction. So let me put in the k hat. And this is a dot product, right? There's a vector dot product in this integration. So k hat dot k hat is 1, so they disappear. And what's left over is I've got the 1 centimeter width on the area strip. So let me take that out with this other constant. So 2 microcoulombs centimeter cubed times the second, and I'll take out a 1 centimeter factor, right? Part of the area. But then on the inside of the integral, from 0 up to 1 centimeter, there is dy times y. Right? So that's what's left over. And then if you continue, the integral of y dy is y squared over 2. And then out here, though, I've got a centimeter and this constant still there. Definitely something I can do with the units, but I'll wait a second to do them later. Over here, this is, the integral is y squared over 2, but you have to evaluate at the bounds. It's from 0 to 1 centimeter, right? And this is multiplied. So you can see there's some cancellations that are nice. The 2's cancel. 1 factor of the centimeters on the bottom cancels with that. But the thing is when I put in the 1 centimeter into y, it gets squared up top. So I got, right, let me do some cancellations with a different color. So I've got centimeters is going to cancel with one of those. So I'm left over with 2, right? And then this 2 and this 2 are going to cancel. And so a midway step, we're not finished, but it's going to get microcoulombs per centimeter squared, right? There's the 2, but don't forget the seconds. That's that. And then y squared goes to 1 centimeter squared. Right? But I've already canceled the 2. And you can see that, go different color. Those things cancel. And I get microcoulomb per second. And I got I. So how come I don't have any numbers? Right? Is this the same thing as getting 0? And nobody's tricked by this, right? It's not 0. This is the same thing as 1 microcoulomb per second. It's just because I chose certain numbers, right? So this 2 ended up canceling the 2 that shows up in the denominator from integration, right? So I'm a teacher, so I get to choose values such that answers are simple. But, you know, in homework problems and quiz problems, you would likely have a scenario that's more realistic where the numbers aren't just 2's and 1's, right? But notice that the units are nice. This is 1 microamp, right? Microcoulomb per second is a microamp. Okay. Yeah, so this is the idea of the current density, which gives us a microscopic model of current. And that's the point.